Analytical Chemistry 1, Lesson 4. In chemistry in general, and in this course in particular, we will be working with a lot of solutions whose concentrations need to be prepared, measured, and reported accurately. You're probably most familiar with molarity as a unit of concentration. It is an amount per volume. Specifically, it is moles of solute per liter of solution. It has the symbol capital M. We could weigh pure samples to high precision and measure volumes to high precision, so molarity is widely used. However, when temperature or pressure changes, the volume changes and hence the molarity changes. One has to be careful of changes in the lab temperature when one makes up a solution and when one uses it. You are less familiar with molality. The symbol is lowercase m, which is moles of solute per kilogram of solvent. Not solution. Note the difference between solvent, solute, and solution. Here the mass doesn't change with temperature and pressure, and so molality is a more stable measure of concentration. But weighing is a more demanding activity than measuring volume, so molality is not used until very precise measurements are needed. We will commonly use molarity in this class. Just bear in mind its limitations. Another kind of concentration measure uses a ratio of solute to solution. The most common one measures the weight of solute. Now careful, this is not moles of solute that are found in a weight of solution. If you use the same weight measures, grams per grams, kilograms per kilograms, the units cancel. You would say that there are so many parts of solute per parts of solution. One reports this as pp, or parts per. If we use micrograms of solute per gram of solution, then we could multiply it by 1,000,000 and call it ppm. We can also find weight of solute per volume of solution. A WV measure finds some utility, but it is important to carefully report the units used for both measures. Otherwise, some ambiguity and confusion can arise. There can also be a volume per volume measure, useful when liquid solutes are being dissolved in a liquid solvent. If you multiply these ratios by 100, you could call that parts per hundred, but we also just call that percent. This is the same kind of measure. If the concentration is lower, a multiplier of 1,000 could be used to give parts per thousand. We commonly encounter a multiplier of 1,000,000 when concentrations are very low, and we report this as parts per million, or ppm. And very dilute solutions can even have a multiplier of 1,000,000,000 to give us parts per billion, or ppb. Here's an example of how these concentration measures can be used and are interchanged. Sulfuric acid is a very important chemical reagent. It is possible to produce a mixture that is pure sulfuric acid, but under the temperature at which it is usually prepared, it decomposes to water and sulfur trioxide, a gas that bubbles away. As such, it is most often only feasible to prepare a concentrated acid that is 98.31% sulfuric acid. The rest is water. Its molar mass is 98.079 grams per mole, and its density at 20 degrees Celsius is 1.8217 grams per milliliter. With this information, can you determine the molarity of the solution? Well, the mass of the solution comes directly from the density. Since molarity is per liter of solution, we find the mass per liter to be 1821.7 grams per liter. We know that 98.31% of that mass is actually sulfuric acid. Therefore, the mass of sulfuric acid is 1790.9 grams per liter. For molarity, we want moles per liter, so dividing by the molar mass of sulfuric acid gives us 18.26 moles per liter, which is just 18.26 molar. Concentrated sulfuric acid is 18.26 molar. Now we need to pause here to teach an important point about mixing and diluting acids in general and sulfuric acid in particular. Now this is a safety test. What is the correct way to prepare a diluted solution of acid? Here are your options. Do you add the water to the acid, or do you add the acid to the water? And should you mix them quickly or pour the second liquid in slowly, and why? The answer is to always add acid to water. The solvation process is very exothermic. If you add water to acid, the little amount of water can be heated to its boiling point and splash hot acid on you. Not a good idea. And add the acid slowly so that the heat can be dissipated. Stir it to distribute the heat. You'll still be surprised at how hot the beaker can get. Be prepared to be surprised. If you grab the beaker, you might be startled and drop it and have a serious acid spill. Okay, remember the safety concern. Let's return now to the dilution process itself to see if anything unexpected might be happening. Take 1 liter of concentrated sulfuric acid. Recall that it is exactly 18.26 molar. Add it to exactly 1 liter of water. This produces our solution of sulfuric acid that is diluted by half. What is the final volume of the diluted solution? Is it exactly 2 liters, or is it more or less than 2 liters? Well, it turns out that you would measure only 1.887 liters, considerably less than 2 liters. Why is this? The interactions between the water and sulfuric acid molecules are stronger than the interactions between water with itself and sulfuric acid with itself. The number of and the kind of interactions obviously changes with concentration. The increasing strength of interactions draws the molecules closer together and decreases the volume of the solution. This is a common situation. Solution volumes do not usually add directly when mixed together. The same happens when a solid is added to a solvent. The volume might increase or it might decrease. You have to watch for this. So what is the concentration of the solution? Well, if the solution volumes are additive, we expect the concentration to be 1/2 of the original, or 9.13 molar. Do you expect it to be 9.13 molar, or will it be larger or smaller? Well, the moles of solute hasn't changed, but the solution volume is smaller, so the concentration should increase above what we would naively expect, and this is what is found as it is 9.962 molar. Now there's another issue with solutions of which you need to be aware. The diluted sulfuric acid, which we just made, was produced at 20 degrees Celsius. As with most liquids, as the temperature drops, the volume decreases. Therefore, the molarity must increase. At 15 Celsius, the solution concentration would have increased to 9.991 molar. In the other direction, a warming solution leads to an expansion of the volume and a decrease in the concentration. Here, at 25 degrees Celsius, the concentration has decreased to 9.934 molar. If it rises to 30 degrees Celsius, the concentration becomes 9.906 molar. You can see, if we are carefully performing precision concentration studies, we have to watch the lab temperature carefully. But notice how the molality of the solutions does not change with these temperature changes. This is because while the volume expands upon heating, the mass does not change. This is the main reason precision work would start to deal with molality instead of molarity. For our course, we will work with molarity just so that you can learn to work with precision glassware. We will look at one more thing about solutions such as these. Let's look at what happens with a 1 molar sulfuric acid solution. We use the label of concentration of H2SO4 and claim its concentration is 1 molar. Funny thing though, there's in fact not any H2SO4 molecules found in the entire container. Sulfuric acid is a strong acid and its first equilibrium constant is essentially infinite. The molecule is ionized and any sulfur in the solution is present mainly as HSO4- ions. It's called the bisulfate ion. And there is also just as many H+ ions liberated into the solution. But what about the remaining hydrogen atom on the bisulfate ions? Is it also acidic? Well, indeed it is. But the salt bisulfate equilibrium constant is finite. It's around 0.01. So there's also some further dissociation to produce some sulfate ions. Those are the SO4- ions. Later in the course, we will see how to work out the concentration of each of the species present. Suffice it to say, under these conditions, the concentration of the various species present are virtually 0 for H2SO4, about 0.99 molar for HSO4-, about 0.01 molar for SO4-, and about 1.01 molar for the H+ ion. This is a common situation in solutions. We make up a solution of sulfuric acid and it turns out to not contain any sulfuric acid, just bisulfate and sulfate ions. And yet the sulfuric acid must have some meaning. The fact we added sufficient sulfuric acid to make a 1 molar solution if it had not ionized is commonly denoted by a lowercase c. This is often called the analytical concentration. An older term is the formal concentration. The solution is formally 1 molar in sulfuric acid. Indeed, you may find that some describe the concentration with a capital F in place of the capital M. You could say that the concentration is 1 formal in sulfuric acid. The analytical concentration is based on the moles delivered to the solution and might also be called the formal or even the total concentration. Certain analytical experiments are only sensitive to this total concentration and is what will be measured. Other experiments are sensitive to the specific species. It might distinguish the bisulfate ions from the sulfate ions. The species concentrations are what we saw before. It is virtually 0 for H2SO4, 0.99 molar for HSO4-, about 0.01 molar for sulfate, and about 1.01 molar for the H+ ion. When dealing with solutions, never forget that molecules may dissociate and ionize, which depends upon concentration and temperature changes, and that can affect the molarity concentrations. And in addition, volumes do not usually add together when mixtures are formed.